let me first introduce, before introducing the presentation, I can introduce, so I am working currently, I'm leading a team in, well, what we call the research team, mostly interested to transfer learning techniques. And the subject of the presentation is about transfer learning. So it's a team composed of most of the people have done a PhD in machine learning, or they have experience in the industry in machine learning. Some people are also engineers, and we are trying to target interesting industrial use case. I will speak about here a specific industrial use case. So the domain of so Criteo business is in the advertising space, and mostly what we call retargeting. So retargeting is something that all of you guys know. We all have basically been subjected to. We have seen that on internet. It's when you go and start doing some shopping or start browsing your website, a specific merchant website, and you don't specifically buy an item, then you suddenly start seeing all over the places when you browse the publisher advertising. So this is called retargeting, and the technology used to do that is tracking your browsing behavior through the internet and retarget you specific ads. So this is used to fund publishers. So publishers, most of the publishers are funded through the advertisements, and the advertisers are paying campaigns to make sure that you will buy their product. So that's the way it's that's most of the Criteo business is called retargeting. It's relying on what we call third-party cookies. There is what we call right now at the moment the cookie apocalypse. If you look on internet about it, so all the advertisement space, online advertising space is kind of redefined. It's a lot of challenges going on around that. And so Criteo and other company need to reinvent themselves and to target a new objective in the advertisement. So now let's go to the presentation itself. So the presentation is a joint work. So here you see my name on the slide because I'm the presenter, but and I'm the team lead. But it's a joint work with 3 other researchers: Matthieu Kirchmeyer, which is a PhD student doing partly his PhD with us in Criteo, and then 2 professors. We have Alain and Patrick Gallinari. Patrick Gallinari is professor at the Leipzig University in Paris, and that's a joint work we did together. So the subject of the talk is about unsupervised domain adaptation with non-stochastic missing data. So don't be worried. I will be defining what I mean by that exactly. And also feel free, please, to interrupt me at any point if something is not clear. Well, I'm kind of stuck here. Sorry. I'm trying to go to the next page, but
can you use the arrow buttons, for example?
Yes, this works. Okay. Thank you, Bala. So let's define what we mean first by incomplete data. So a typical use case is, for instance, concrete use case is when you try to diagnose a disease. For instance, the case of Alzheimer. So a person that has Alzheimer disease, so to diagnose if you have or a person has Alzheimer or not, it will go through different treatments. And most of the time you will go through an MRI scan, but you may also go through something that is more precise than MRI, which is called the PET modality, that will require you to be subject to some radioactive substances. And that, of course, causes problem because it may have health issues on the subject. and we would prefer to avoid that if necessary. And one of the big challenge in this domain is we would like to be able to say if you are subject of, if you have Alzheimer with a high probability without you needing to take the PAT modality test. And therefore, you would like to be able to somehow reconstruct the PET modality from the MRI modality, but not with the goal to reconstruct it exactly, but with the goal to finally diagnose, so the goal of classification. That's a concrete use case where you have a classification problem with some missing data problem. And this is the kind of use case we are interested to. And here I'm giving some references on this kind of research. In the case of computational advertisement, so why are we interested by this problem? So I was speaking about the retargeting problem. So the retargeting problem is when a person is browsing a specific domain, then you are collecting a lot of features on a user, and at some point you have to decide, you have to take a decision to show a display, an advertising display to that user based on the feature you have on this user, and based on contextual features like what is the moment of the day, what is the publisher website the user is on. When you take that decision, you will use a lot of features you have on the domain the user browse. This is typical advertising retargeting use case. The industry is also interested to acquire new users. So when if I have a website, for instance, with many customers, I would like to grow my customers. So I would like to be able to target specific advertisement to users that never visited my website. And as an advertising company, we would like to be as good in doing that job than as in the retargeting business. We would like to be able to use somehow the same model that we use for retargeting for this kind of prospecting use case where we will prospect new users. But in this use case, you see that it is different because there is many features in this kind of prospecting use case that doesn't exist, because if you want to address new users, then you don't know what is the user browsing activity on your website. You don't know how many, for instance, products he has been browsing, what's the time he spent on your website, and so on, because he never came. And therefore, you would like to somehow infer those features, and you would like to know what would have been those features if the user would have browsed my website. And this is why it's missing. And in that case, you still want to predict the probability of click, for instance, to take a decision. Do you show the display or to bid in the advertisement space, but with the possibility to infer those features. So this is the use case of that we are interested by in the computational advertising. So what's important when we speak about domain adaptation is there is this notion that is common to any domain adaptation problem, which is the shift of distribution, what is called sometimes covariate shift or sometimes target shift, which is basically the distribution change, the distribution on which you are training your data and the distribution on which you will apply your model would be different. And this is typically the case in the two use cases that I explained to you. And therefore, you need to somehow be able to accommodate for that. You need to be able to change the distribution or transport the distribution, or be able to change, to have a model that take into account that the final distribution on which you will apply your model is not exactly the distribution that you have seen in the source, right? And that's the main problem domain adaptation is trying to target. So what is the scope of this work? So the scope of this work is three points. So we are considering as I said, the unsupervised domain adaptation. I will explain what I mean by that. So first, there is a missing part, and the missing part would be in the target domain. So if I go back to the slide here, the big cross here, it means that there are some missing parts in the target domain. So the domain that we want to serve, right? On that domain, there are some missing features. The second thing is that we consider that there is no possible supervision on the target domain, meaning that we don't have any label or enough label on the target domain, because should we have more labels on the target domain, then there is no need to do any kind of domain adaptation, because you have enough data on the target distribution, and you can try to learn directly. So this will be beneficial if there is few labels on the target domain, and in that case, it will be beneficial to transfer information from some other domains. So no possible supervision on the target domain, and there is a notion of domain shift, meaning that the distribution between the source and the target differs. And here it's clearly the case, because as you see, there are features that are missing, and even for the non-missing feature, the user behavior may be different and may explain a shift in the distribution of the features. So those are the 3 points we want to address at the same time. And for that, we will basically design an adaptation and imputation mechanism. I will explain what I mean by that to address this problem. And I will also explain what is the kind of mechanism we are, what is the hypothesis we believe explain the missingness of the data, because in that area of research about data missingness, there is different hypotheses that you can consider. Here we consider that the data is non-stochastically missing. I will define that more precisely further. So to summarize the contribution, we are doing this UDA, so unsupervised domain adaptation, jointly with an imputation mechanism for the missingness part, in order to classify, in order to take a decision. So the goal for us is not to reconstruct for the sake of reconstruction, because that's also a big part of the literature. No, here the goal for us is to reconstruct with the objective to classify. So we don't really care too much about what are the value that we will infer. And we propose a model that will target the problem end to end. So the model that will take the final decision, which is deciding if the subject has Alzheimer or not, or basically predicting the probability of a click in the case of advertisement. And we will propose different evaluation academic benchmark on different real world problems, as well as academic problems. So some related work on domain adaptation. So domain adaptation, we can divide the related work mostly in 2 parts. One part is trying to weight the observation during training. And that's typically the case when you know in advance that the source domain and the target domain differs, for instance, in the class distribution. That's very typical. When the class distribution differ, then you can do a simple reweighting mechanism in order to change your expectation that from the source to adapt it directly to the target expectation. So that's a common trick that end up to reweight your individual observation. The second part, which is mostly what we consider here, is to try to learn a projection or a mapping, right? In order to project the source to some intermediate space, and the same for the target, an intermediate space where there will be no possibility to differentiate between the source and the target. So you want to learn a kind of embedding space where the distribution after embedding between the source and the target cannot be differentiated, and therefore you kind of use what we call GANs, so GANs mechanism, generated adversarial network mechanism, where basically that mechanism has been used a lot. I'm sure you are aware of it in images, where you try to learn somehow an image or the distribution of an image, starting from a noise, so from a random noise, from a normal distribution, and you learn that mapping, and you learn that through a GAN game. So what you try to do is you have a discriminator that try to distinguish is your data coming from a real data, is it a real data point or is it a fake data point? And you have a generator, which is the mapping that try to learn this mapping from the noise source to the intermediate space. And the generator try to fool the discriminator. So through this kind of min-max game, you will be able to learn a mapping from source or from noise to the final data that will finally generate something that is very close to an image. Here, it's very related to the domain adaptation, just that the source is not noise, but it's a real distribution. So you have, instead of having fake data, you have, for instance, the target distribution, which is the real data, and you try to project that target data to an intermediate space in order to fool the discriminator, and the discriminator will try to distinguish between the source and the target. And at the end of the day, at convergence, you need to reach a space, a point of convergence where there will be no possibility for the discriminator to discriminate between the source data and the target projected data. So it's the same mechanism applied for domain adaptation that we will use it, which is called adversarial mechanism. And then there are other extensions of this mechanism that try to explore directly distances, because you can see that GAN mechanism is actually can be rewritten as optimizing some Jensen-Shannon distance, and you can try to directly somehow model the distance between the source and the target through some typical, measures, distance measure between distribution, for instance, the Wasserstein distance, and you try to minimize that distance. So there is some kind of related work that try to target the problem in that direction. So with regard to the imputation mechanism, so again, there have been many approaches. Most of the approaches consider that the missing data is missing following a stochastic process, which means that you could try to exploit the stochastic process of missingness in order to learn from it. In our case, we consider that it's completely missing. Data is completely missing, always completely missing. So there is no stochastic process that you could exploit. And also most of the imputation have been done in the original feature space, which means that most of the people have tried to consider what happened. You basically reconstruct and you look at the reconstruction and you try to see what's happening in the reconstruction. Here, as I explained, we are not interested to the imputation has the value that are imputed itself, but you are interested to the decision that is taken after imputation. So we have, to summarize, imputation for classification. We are doing the reconstruction in the latent space. As I said, no supervision possible on the target space. And the missingness is not following a stochastic process, which means that we cannot exploit any kind of statistics from the missingness behavior. Another part, so just to finish the related work, another part related to imputation is that people have tried to use GANs as well for imputation, because of course, so as I explained, GANs mechanism is a mechanism to somehow map distribution or to learn a distribution. However, what people have shown is that this kind of generative modeling, which is using GANs, or you can also use variational autoencoders. So those kinds of mechanisms are not sufficient it's not enough to be able to reconstruct correctly. So you need to add some other mechanism like a mean square error loss, which is typical for reconstruction term, or you can try to do what people have done in cycle GANs, which is basically trying to infer or to reconstruct this target distribution from the source distribution, but you can also do the other way around, which is trying to learn the source distribution from the target distribution. And if you introduce this kind of cycle, then it happens that it works better for this kind of use cases. So now that I've introduced all the related work, so let's go into our model that we introduce here. So what you can see on the left side is, on the left bottom, you have XS2 and XS1, and you can see it's a digit. It's actually the digit 8 that is divided in two parts, the bottom part and the up part, right? Which represent the fact that on the source we have all the data available, right? But it maps to the target XST1, and XT2 is not available. So this is the setting. So we observe only one part of the target, which is XT1. We don't observe XT2. And so somehow the intuition is you would like to be able to infer XT2, and how you would do that, you would try to exploit the relationship between XS1 and XS2. So that's the intuition. So the first thing that we want to notice here is that the missingness, so as you see here, this is what I'm defining as missing completely at random, doesn't depend on the data itself. So meaning that the part that is missing in the digit is always the same part, whatever the digit you observe. If you observe a 7, an 8, whatever the digit, it will always be the same part. So this is the hypothesis of work we are working on here. And this is why we call this mechanism missing completely at random. So that's the first thing, meaning that there is a binary mask that is fixed and that is always applied. The second point here is that we make the hypothesis that you cannot fully reconstruct the missing part from the part that you can see. Concretely here, if you look at the 8 digit and you look only at the top part of the digit, you cannot construct the bottom part of the digit. So here XS2 is an 8, but if you look at XS1, it could have been a 9, right? And therefore, it's not enough to, you cannot only rely on XS1 to reconstruct XS2. The third hypothesis, which is very important when you do domain adaptation, is that we suppose that the probability of the missing part giving the part that is non-missing is invariant between the source and the target, which means that you will try to exploit, of course, this PS of X2 given X1 to use it for the target. If this hypothesis is not true, you cannot do much. So you have to rely on this hypothesis in order to be able to somehow reconstruct XT1. And then we finally assume that we can find a classifier with the low error both on the source and the target. And so just to comment a bit on the model here, so before going deeper in the loss function, so as I said, you have so XS1 and XS2, which is the input digit that you observe on the source, right? Then on the target, you observe basically just XT1, right? You want at the end to be able to take a decision. For instance, does the guy has Alzheimer or not? And to do that, you will need to infer the missing part right here. You need to infer. Of course, this model will be applied not on the source, because for the source you have, of course, the missing part. You will apply it on the target. And so to do that, you basically learn somehow projections. Here we call that G1 and H, such that you can reconstruct the XS2, the missing part. So I will go now in the details about how we do that. So feel free, please, to interrupt me if would you have any question. Huh? So the first part of the loss function is what we call the adaptation loss. So the goal of the adaptation loss is to make sure that what we call XS tilde here, so the final projection of the source in the latent space, has the same distribution as xt tilde, which is the projection of the target in the latent space. So you would like the final projection of your target distribution in the latent space to be the same as in the source space. Why you want that? Because at the end, if both spaces are, if you cannot distinguish between both spaces, or if they follow the same distribution, then you will be more, you can ensure a better decision. Then your decision, your classification decision will be based on some domain independent feature and will not be biased by the specific domain on which you have trained. And to do that, you use this, what I already explained it, the adaptation mechanism, which comes from a generative adversarial network, where in the one hand, so it's typical, it's a typical cross entropy loss, where on the one hand, you want to be able to distinguish between your source data and your target data. That's typical classification. But on the other hand, so this is what you try to maximize. But in the other hand, you want to learn G1 and H, the projection, in order to fool the discriminator. And that's why you have a mean here on parameter G1 and H. So you really try to learn those projection in order to end up with the latent space that is somehow domain independent. So that's the first part of the loss. The second part of the loss function is concerned with the imputation part, which we call the imputation loss. So the imputation loss would be basically what you see here. So as you see, you have tried to somehow generate XS2 tilde, which is your imputation of X of the missing part of XS, right? XS1, which is XS2 tilde. You try to generate this, and you have the ground truth of this, which is basically what you observe on the source. You know what is the ground truth, which is this. And so you would like those, the generated missing part to be close to the real part that actually is not missing on the source, it's only missing on the tilde. So you can measure that using a reconstruction error, which is what we call by MSE. And on the same side, meanwhile, at the same time, you also want the distribution of XS2 tilde to be close to the real distribution observed, which is XS2 hat. And therefore, you also use an adversarial loss, which is the same as before. So you combine those two losses in order to be able to reconstruct this missing part of the digits that is as close as possible as the real part of the digits in terms of reconstruction loss, but also in terms of adaptation loss, which means in terms of distribution. And the final part is the classification, which is basically you have a task, as I said, at hand, which is, for instance, diagnosing, so classifying is the subject to Alzheimer or not, or what is is there a click or not in case of online advertising. And this is basically a loss function that you apply on your final embedding layer or final projection that you apply here. So yes, so let's now go into the experimentation. So we used to experiment. The first one is on a very common digit datasets that are used in most of the domain adaptation papers. You will see those datasets. Those are digit datasets where you have a source and a target, and the difference between the source and the target would depend on the dataset. And sometimes the distance can be very big. So for instance, here, if you look MNIST and MNIST-M, so those are digit datasets, and MNIST-M is just applying some new background and new coloring of the digits. But if you look at here SVHN, so those are street numbers taken from Google Street View. And if you want to, if this is the source, you see that the Google Street View are really the numbers of people they have on their house, right? And those differ a lot from MNIST, where it's really handwritten numbers, right? And so that's a task that is way more difficult. And you try to see if you can recognize the digits without supervision on the targets, knowing the supervision on the source. So that's typical things that are really nice to test to which extent you're able to do well in the task. So let's present here the results. So we have different projections, so different source targets. So here the source is MNIST, the target is USPS. So USPS is the US Postal Service, and in that case, I don't know if I have example of that, but it's very, I would say, very close to MNIST. But if you consider Google Street View, it's way more difficult task, right? And so the first baseline here are, so the naive baseline is what would happen if you train completely on the source, right? And you use that model for the target. Here, that means that you make the hypothesis that even on the target there is no missing data. In that, of course, it's not true, but this basically allows you to have some kind of upper bound of what kind of result you can reach. So if you suppose there is nothing missing and you train only on the source, and here if you still suppose that there is no missingness, but you adapt, you still do the adaptation because the source and the training, even if there is no missingness, differ in distribution. And you first see the first thing that you can see on the baseline is that clearly the adaptation mechanism help in all cases to improve kind of drastically the performance. Then the real question is, okay, that's nice, but what happened in the real world where there is missingness? Then a first mechanism that many people use, and that is actually a super bad mechanism, is to just to use 0 for imputation. That's really, really bad. And you can see clearly that if you use 0 if you just use 0, so you take the source model and you use 0, okay, then you see that the performance is super bad. You can still keep using 0, but use the adaptation to adapt the source and the target distribution. Then there is improvement, but still not great. So using 0 for imputation is clearly not a good idea. Another idea is to completely ignore the missing data. What does that mean? It means that you use your model will only use the features that are available on the source and the target, and you consider that, okay, you don't consider the missing data. And of course, if you do that, that's already better than replacing by 0. And again, adding an adaptation mechanism help, right? Quite well. And then the final row is what happens if you use the mechanism we introduced, which is imputation plus adaptation. And you see that it constantly improves depending on the task. Some tasks are easier and some tasks are more difficult. And clearly, when the task is more difficult, the adaptation imputation mechanism give you way better or higher improvements than when a task is easy. So that's more or less it for this use case. So now let's go to the advertising dataset. So the advertising dataset, so it's mostly the dataset I introduced, what I show you in the beginning of the presentation. So you have a source domain. The source domain is what represents retargeting, which is the user is retargeting to a merchant he already visited, which means that we have user data, historical user data. And the target domain is user is target to a new merchant, for which we don't, there is many features that are missing, and we have only the contextual features. The label is basically, did the user click or he didn't click, right? So this is what you try to predict. And what we see here are the results on the different mechanisms. So here, the source only, we couldn't use it. Why? Because source only means that make the hypothesis that you apply it on the target, and then there is then you can use it when there is no missingness. But here there is missingness, And since it's not a benchmark dataset, we don't have those missing features, so we cannot apply the source only dataset. We can only apply the real. We have to face the missingness mechanism through different use cases, either by using the zero imputation, or you ignore the missingness, or then you use our mechanism. So this is a log loss, meaning that lower the value, better it is. And on two datasets, ads Kaggle is a dataset that has been released, it's publicly available, and ads real. So the difference in scale between the numbers of the left column and the right column is due to the fact that the positive negative ratio between both datasets are not similar. So the number of clicks, the proportion of clicks on the ads Kaggle dataset is not the same as in the ads real dataset, and this is because those are the ads Kaggle is a public dataset, and we don't have control on the way the dataset was generated. What you can see is again the adaptation imputation mechanism help clearly in inferring a better take a better decision of was the ad click or not. So if we go now more into the details in the different use cases about different losses. So if you remember, I can go back to these, right? The loss was divided in adaptation loss, L1, this imputation loss, L2, and the classification loss, L3. And the imputation loss was itself divided into one parameter for weighting the mean square error and one parameter to weight the adaptation mechanism or adversarial mechanism in the imputation loss. And here we try basically to do some kind of analysis of what's happening. So are the three parameters of the loss necessary? So do you really need the L1 part that try to align the source and the target? And you see clearly that yes, you clearly need it. And the second question is if you look at L2, how much do you need of the mean square errors versus adversarial? And you see that actually you need both. If you just do a mean square error mechanism, it works well, but adding a bit of adversarial help improving mostly the result in all the use cases. And here you can look deeper at the different value of the hyperparameters. Okay, so to conclude here, what I propose is to model jointly adaptation, imputation in classification. We have seen that in the case of non-stochastic missing data, you can solve that with the combination of regression loss and adversarial loss that help basically improving the results. And this has been demonstrated on two data sets, synthetic data and real world data sets. So what are the next steps? So the next step is if you check mostly what's happening here, we are considering one kind of shift, which is called the domain shift. What I mean by the domain shift is that the P of X given Y is not the same in the source and in the target. And what you try to do is basically take that into account. But if you look at your joint distribution, which is the PXY, the PXY has two components, which is the PX given Y and the P of Y, which is the label shift. Or you can look at it from another point of view where the P of XY could be divided as P of Y given X times P of X. So which means that there are different, when usually you consider the shift of distribution, you have to, most of the people target one kind of shift, but they don't target the full shift, which is actually very hard to do. But some interesting research is done currently on generalized shifts or generalized target shift, where you try to consider the shift in the feature distribution, but also the shift in the labels, meaning the proportion of labels that you observe in the source and in the target. That's very important, especially in advertisement space. Why? Because the probability of a click in a retargeting is typically higher, way higher than the probability of a click in the prospecting space where you try to target new users, and therefore you would like to be able to take that into account. Okay, that's it here. So I'm open to take any of your questions. Would you have questions?
Thank you, Amin. Very clear presentation. Any questions?
All right, it's Flora here.
Yes.
Thanks for the talk. I'm just wondering, have you looked at cases either zero shot or few shot domain adaptation, especially when your target domain don't have much data?
Okay, so here we are, okay, just to specify, to be more clear, here we are considering the use case where we don't have supervision on the targets, but we are considering that the classes are known in advance on the target. So we are not considering, maybe it's what you are referring to which is the case of no shot or few shot, where there would be new classes.
Yes, new cases. Yes.
Okay, new classes on the target space. No, we haven't considered that. We are trying to do some work on NLP on this. Use case is when you try to annotate. Typically, when you have a product database and you try to annotate products with so detect from product description features of products, which is, for instance, is the TV, is it plasma TV, is it that kind of TV? So it's important when you pass product datasets to be able to detect features that are piece of text that describe the product. And in that use case, we would like to be able to detect new descriptors that we didn't know in advance, which is exactly the use case of few shot or no shot. But in that use case, we are using completely different kind of system, and we haven't used I haven't seen anything in the unsupervised domain adaptation. It's mostly applying NLP methods for transfer learning that are based on transformers and BERT technology and things like that. Yes, so I don't know if it's so that's my reply to your question. So we haven't investigated more than that.
Yeah, I'm happy to send you. There's a recent archive from our group that are working on few shot domain adaptation, but that's more on spatial temporal data. May not be completely relevant. One thing that I wonder is the interplay of those three losses.
Yeah.
You have that were jointly learned. Did you have any ablation study on the contribution of each of these, whether they even okay, yeah, whether any of these in combination have some sort of like min-max problem, I guess, in terms of the effect of the performance?
So, well, the ablation study we did is the one I presented here, where we see the impact of each part of the loss independently. So we did ablation study to study, okay, what are the effect of the L1 loss, and we see that it's working, and also what is the effect of the parameter on the L2 loss. So this is the study we did. But that said, there is many problems here in this kind of study or any ablation study related to unsupervised, how do you say that, in this setting where we suppose that there is no data no supervision possible in target space, is that we can do those kind of study because we have the finally we have the ground truth right on the target space, and we can measure the performance. The only problem is that in practice, if you want to put those kind of stuff in a production system, you don't really have the how do you say that? You don't have the targets missing data, and so you cannot really take any decision in that case. But we did, so to reply to your question, we did kind of ablation study. We have seen that when there is the interplay, so it's clearly beneficial to have the three together with specific hyperparameters value. But we haven't observed. So the question about especially when you start doing GANs, it's you have to be very careful on how you control the mechanism to be sure it converges. So that's something that Matthieu, which is the PhD student, have done. But what I know from discussion I had with him is that it's not obvious, of course, to make it work. You have to be very, very careful, and in that sense, yeah, there are maybe some point there to be careful about.
Thank you.
Hi, this is Xichan here. Could you hear me?
Yeah, I do.
Yeah, can you go back to the slides about the architecture? I have like 2 questions. Yeah, here, like my first question is about, so you got like samples from 2 domains, source domain, target domain, but you apply the same models on them, G1 and H. I mean, like, does they share the same parameters?
So yeah, so here
yes, let me like rephrase that. Because you have like samples from 2 different distribution, S1 and T1, by applying the same models, that so your models here is trying to make the G1 and H can map samples from 2 different distribution to the same, because you're using that discriminator in adaptation. So I'm kind of confused here.
Yes, very good question. So if you look at yeah, so you are basically trying to, so let me go one by one. So here you try to align the source, right, the XS and the XT, right? So you try to align the source domain and the target domain. So yes, yep. G1, and there is only one G, which is so you are using a part of the target domain, right? You don't know the supervision of the, you don't know, but you know you have some examples, right? And you are using that to basically learn a kind of projection, which is G1 and H, and this projection will be so. Your question is why G1 is not different from why G1 is the same. This is the question. Why is it not different? So the G1 is the same for the how do you say that, for the apparent part. So you have G1 for the upper part and G2 for the missing part, but it is the same because at the end of the day, you will try to reformulate G1 and also H in order to reach this balance in your min-max problem. You could try to use another G. People have tried that, so you could try to use a G3 if you want. But we from the test we did, we observed better stuff here. So somehow it's a kind of regularization, or you are reducing the space of parameters. So you are using the same parameters, yes, for XT1 and XS1. So it's the same parameters, which can seem a bit confusing, but it's the same parameters that are doing this projection in the in the final space. So it's the same parameter for G and the same parameter even for H, even if for H it will be learned mostly when it will play a big role in this imputation loss. So the
okay.
H is mostly trained on the XS, but G1, yes, it's also trained together with the part that is observed in the XT1.
Okay. So my second question is here, because the introducing the D1 and D2, is there like any trick you can share, like how you manage to, because this thing is quite delicate, can you share some tricks about how you're getting the convergence about this scan learning phase, in the scan learning phase?
So okay, one of the things that so here here you see the OT. Okay, I didn't speak too much about OT, but OT comes from optimal transport. So okay, I know that if you look at the literature of GANs, you have this Wasserstein GANs, which are another way to basically to ensure better conversions of your GANs. And so we have used that, but in this specific setting it's not me that did the experiment. From my discussion with Matthieu, we didn't have particular that many problems, maybe because of the kind of distribution that we were dealing to are already right. It's because most of the problem that you will observe with GANs is when the mods, when the mods of the source and the mods of the target do not align. So if you have a distribution in the source that has way more mods than in the target, you will have problems, which is not the case here, because in the case of the digit dataset, there is 10 mods.
Yeah.
So we haven't considered the use case where the target has more mods than the source, which is a future work we want to go for. But that will be way more complex, even in terms of yes, you will need to handle this. That said, there is recent literature on trying to deal with the mods. So instead of using GANs, you can use some kind of generative model optimization, like for instance variational autoencoders, which are interesting because you can directly minimize the likelihoods, which you cannot do in the GAN. So when you can minimize we can minimize the negative likelihood, then it allows you actually to not fit in that specific problem of GANs that have this setting. That's why one of the things we would like to go through is going through not through GANs, but through an explicit formulation of the likelihood, something that you can explicitly target and minimize. And yes, so that's the direction we are trying to take right now.
Okay, thank you.
I have a question, but a more general one. I was just curious. I'd read in a few sort of machine learning press articles that the whole COVID-19 pandemic had caused a lot of the learning algorithms in a lot of systems to need to be manually retrained. And I wondered if you encountered any of this. As the sort of the pandemic kicked in, did you find that a lot of the models that were trained to work in, advertising domains over the last few years, as 2020 got going, did anything change, or did they all adapt quite effectively? So I guess it's a domain adaptation, but a sort of a temporal domain adaptation question.
Well, honestly, in our business use case at Criteo, we haven't observed this kind of phenomena, maybe because the system is kind of retrained automatically kind of often, which means that we we are actually already accommodating for changes in user behavior. So if there is a user behavior change, since the pace of retraining is kind of fast, that may just circumvent the problem. So we haven't observed this kind of use case, even though there have been changes in user behaviors. That's for sure. We have public data about we are publishing information about user behavior change during COVID-19, especially shopping behaviors, where you can see that people start shopping more, some kind of articles, especially grocery, but stop or even technology. So many printers have been sold and many other kind of items, while other items, especially luxury stuff, basically dropped. But our model actually are trained in a fast pace, so we haven't really observed any kind of problem in that sense. I can understand that if it's not trained fastly enough, you could be facing problems. Yes.
And sorry, you said that you've published something about the change in behavior. Is that a pointer you could give us?
Yeah. So we have some public information that we are released every week or 2 weeks. I can send the link about user shopping behavior, which is because Criteo is a lot of information about shoppers on the open internet, and basically all across different retailers. And yes, we have been publishing information on that.
Cool. If I could maybe just ask one other quick question. I've got a PhD student who's been working, my background is really search engines, and I've got a PhD student who's working on recommender systems, and she's been looking at false positive metrics. So worrying about sort of mistakenly showing the wrong thing to people. And we were discussing earlier this week about how information retrieval largely ignores those false positive metrics, largely because I think you just have so many relevant items. Somebody types in a query, you get loads of matches, and actually the problem is too much relevant stuff, not getting false matches. When you're using your metrics in your space, I would imagine that in the advertising space, you're very worried about giving false positives to people. So does that change the way you measure the effectiveness of these systems?
Yes, of course you are worried about. So the different, I mean, we are in recommendation space. Yes, you don't want to show false positive, but the question of how do you define a positive is important. I mean, it's not because you gave the example of search. In the case of search, the notion of relevance is well defined because it relates to a contextual query. So there is a notion of relevance. We are not in that. We are not in the search advertising space. We are in the display advertising, which means that the context is a kind of open to interpretation. So it depends on the user browsing history and what the user kind of do and so on. In other words, it's very hard to judge when you display a specific product to a user, to which extent that's relevant or not. The user, of course, can judge if it is relevant or not. So what we try to make sure is that relates in terms of categorical browsing history and things like that. And we have different way to measure that. The recommendation are close in terms of space and in terms of common features like co-click behavior and different kind of metrics, and then of course metrics of click and non-click metrics. But those are still how would you say that click data, right? Which is not an absolute true versus human-based ground truth that is very common in I would say in search especially search advertising, because you can really judge that, okay, this specific ad relate to the query or not. But in the display advertising, it's I would say it's more blurry in the sense that you except the user, it's very hard for anyone to tell if the advertising is relevant or not. Okay, beyond the fact that, okay, it relates to the fact that the user went on the website, he maybe browsed some related products and things like that.
Cool, thank you. So if I just go on the Criteo website, I'll find these reports about the shopping.
I think yes, I would also look for them and forward them.
Great. If you send them to Barla, then he can forward them to me.
Okay, that's perfect.
Thank you very much.
You're welcome.